Welcome everyone. Final session for today, I believe. We're starting at 3:20. We'll be going to like 5:20.
Yep.
I hope you guys stay with us. Today we'll be talking about TensorFrames and actually how the whole TensorFlow fits with Spark. So I hope you guys stay and enjoy what we have for you. Is that gonna work? Guess not. Can you click?
No, try now.
Try now.
Oh, sweet. I think it decided to screen.
Technical difficulties.
How's that now?
Yeah, there you go.
Perfect.
All right, so the goals for today, as Denny mentioned, we're going to go quickly through what the deep learning is. We're going to introduce a little bit about the feature learning, what is the feature engineering, a very quick run-up of about TensorFlow, and then we'll introduce a model, we'll build a model. Going through the notebooks that we have for you to recognize objects and images. We'll be using the very familiar NIST dataset to recognize handwritten digits. And then we'll be introducing TensorFrames, and then we'll delve into the tutorial side. Very quickly, hi, I'm Tom. I've been around for like over close to 15 years, number of continents. That's pretty much it. That summarizes me. I like big data and the neural networks. Also vacuum tubes, so if you want, go ahead, talk to me after that. After you.
Cool. And hi, everybody. My name is Denny Lee. I am a principal program manager with the Azure Cosmos DB team. But prior to this, I was a tech evangelist with Databricks, and then I was also the senior Director of Data Science Engineering at Concur. Sorry, I can never remember that title. and then before that, I was actually also at Microsoft. I was actually on the team that built what you currently know as HD Insight. So I was on the team that went ahead and said, "Hey, Steve, we have no big data strategy. Let's embrace an open source Linux-based product. You're okay with that, right?" So that's me, yeah, that's it. But we also, shameless plug. If you're into PySpark, Tom and myself actually are the co-authors of the book Learning PySpark. So they're okay. That was our shameless plug. We also want to say thank you. So there are a number of people that we want to thank. One is Tim Hunter. He's a software engineer at Databricks. He helped us a lot to make sure that we got the notebooks right. Basically corrected all the crappy code I wrote. Also Joy, who will actually be coming up here to help us. She has been instrumental in helping us get the stuff done. And Bilal was going to be here, but I guess he skipped out, so we'll just skip him then. So prerequisites for you folks who are going to work with us. You can definitely do everything we have here as PySpark in Anaconda using on your own laptop, no problem at all. The other thing we suggest, though, is actually using Databricks Community Edition, okay? So mainly because the notebooks are already pre-written, pre-set up this way, okay? Now, if you go to aka.ms/PyData TFS, I think I wrote it somewhere around here, but if you go there, basically, you will be able to download all the notebooks and the slides for this session. So the quick call out for you guys is basically go to databricks.com, try Databricks, click on the right side, that's the free one, okay, for you guys, all right? And then sign up, okay? Then just basically go through the sign up process. It's completely free, okay? So for you folks.
Bring back the URL.
Oh, sorry, yeah. Yes, right there, sorry. So if you guys can do that, then that way you can actually not just follow us along, but you can actually run the notebooks themselves as well, okay? All right?
All right.
Cool. Anything else?
So I think this is just a setup.
Yeah, okay, yeah. So, we'll skip ahead. This is just setting up. This is what it's going to look like when you set yourself up. When you sign into Databricks, it's going to look something like this. So just in case you lost the URL.
Just show URL.
Oh, okay.
URL, yeah.
Oh, okay. Did we put it?
I don't think it's there.
Oh, did we forget?
Yeah.
Okay. Okay, where's the, nope. No, it's okay. No, just write it down.
Yep.
All right, so we'll do this right on the fly. Okay, so you are going to get your notebooks from here. You're going to get Databricks Community Edition here. Dope. There you go. you should receive an email that will give you this URL, this bottom one, when you sign up for Databricks, but just in case you forgot, that's what it is there, okay? So those are your 3 primary URLs, okay?
Okay.
We'll hold it for a minute, and then we'll go on.
So we can skip that. Oh, gosh.
Yeah, so
Yeah, I can skip.
just start running, yeah. Cool.
For some reason, that URL doesn't take you to any notebooks.
The AKA MS.
So not even if you're Microsoft.
Oh, it's actually an external URL, so. Did I type it wrong? I'm sorry? Okay. Yeah, so that's basically where you're going to go to, so the AKA one. So just to give you some context, this one's the presentation, though I do need to update it again. And these are the notebooks, okay? You're going to use the IPython version ones. I included the HTML ones just in case you wanted to look at what the output looked like from running it, so that way you didn't actually even have to run it to see what the output looks like, okay? So, all right, so let's move on to the actual presentation portion of this.
Yep.
Okay.
Try.
Yeah, you got it?
Yeah, I got it.
Cool.
All right, so since most of you guys raised your hands that you know what the neural networks are, we're going to quickly go through all of this. So neural networks, in general, they are modeled from human's brain. There's a bunch of neurons. This is a fundamental building block of any human brain. It's called neurons. There's around 100 billion of them, and each of them is connected roughly to another 10K. So this is a very, very high dense graph, if you will. The way they work is, in an essence, the neurons receive the signals from the preceding neurons. These signals can be either chemical or electric. And if there is enough buildup of the signal within the neuron, it will actually propagate the signal further on, in an essence. In a very, very similar form, this is how the artificial neural network, neuron works. So it receives the input from the preceding neurons, gets into the summation function, then passes through an activation function, and then depending on the activation function, whether it depends what sort of signal it propagates. Different types of propagation functions. We have a tan and sigmoid. These are squashing functions. Tan, hyperbolic tangent, will squash that to be the output to be always between -1 and 1. Sigmoid works in a very similar fashion. It's anchored around 0, but it outputs anything between 0 and 1. And the rectifier, the linear, so it outputs anything that is greater than 0 will actually get output. So whatever you get in the summing function in your neuron will get serve as an output as long as it's greater than 0. If I'm going too fast, just stop me.
Right. The one thing, though, definitely you'll see within the TensorFlow notebooks themselves, so is that we actually will be using ReLU. Okay. We'll explain a little bit later why, but basically it's the latest and greatest in terms of which activation function we're supposed to be working with. It actually has to do with backprop. Again, we'll go into this a little bit later, but that's one quick call out there.
Good. Thanks. Yeah. So an artificial neural network is nothing more and nothing less but a collection of neurons stuck together. They can be stuck together just like in this image on the right, into layers. They can be stuck into lattices, like in a coherent network. But effectively, every single of those dots is an artificial neuron. In a simplest model, simplest neural network can consist of a number of input neurons and a single output neuron. And then with this simple structure, you can already build a simple logistic regression, logistic function. It is also probably, I want to call out, is a black box model, because the more complex your neural network gets, the more hidden layers you have, you can't really analyze the connections just like in a statistical model. Come on, there you go. Some examples of neural networks. We have feed-forward networks that actually receive the signal at the on the input and then propagate the signal through the output. We have the radial basis function networks where the neurons have different activation functions, and the recurrent neural networks where you have actually local feedback loops within the neurons or within the layer that help you to generate stuff. There are a number of different learning paradigms, just like within the machine learning. We have a supervised and unsupervised paradigms of learning. The unsupervised paradigms learning you can see at the bottom here, which is the self-organizing maps, also known as Kohonen maps, where you think about clustering models, right? Where you have a segmentation, you are trying to find patterns in your data without knowing what the true data is or what your true target is. If you have your target, right? So you want to either predict or classify your data, you would use either backpropagation, which is essentially calculating error at the output of the network, compares the output of the network with the desired output, with your target, and then that error gets back propagated through your network, and through a network of derivatives, it actually updates the weight connecting to different neurons. We also have a memory-based learning, which is essentially like think about you are a kid and trying to learn different things. This is how you memorize. The network literally learns to memorize the inputs you are presenting it with. Applications are vast, and this is just literally a handful of examples, but you can use them to recognize faces. You can train the neural network to learn to play different games. I think recently there was one of the Atari games got bitten by a neural network. You can use it to speech recognition. So Siri would have one running behind, Cortana would have another one. You can classify objects like we're going to be doing today, but we're going to be doing only like a single object recognition. There are frameworks and there are neural networks, the whole models that actually from a single shot would recognize multiple objects at the same time. Okay, so what the deep learning is nothing really more than a neural network on steroids. So when I presented you with the very simple neural network with two hidden layers, a deep learning model will have multiple layers and also many more neurons within a single layer, right? So in this simple example, or not simple, in this example we have a 224 by 224 input image, which is already a mind-boggling number of neurons in the beginning, right? And then it passes through a number of intermediate layers of convolution and pooling in order to get to your output. Be it, in this case, it might be a classification or it might be a prediction.
Right. So actually, let me just add one quick thing, if you don't mind. So the key facet here is that as we've gotten more advanced in deep learning side of things, the key call out is that a lot of our solutions involve just adding more and more layers, adding more and more neurons to the problem. Okay, so AlexNet is sort of the one we are referencing right now, but the fact is that there's also VZGNet, ZFNet, GoogleNet, and actually the last year's winner was ResNet, okay, which was from Microsoft Research Asia. And so the context is that the reason why we're calling out the 2012 one is because that's when CNNs or convolutional neural networks started becoming, okay, now this has become interesting. They are becoming more powerful. They can solve these problems faster. And so up to this point, we were doing things more like SVM or other algorithms. And so because we thought those were significantly faster. With the advancements of GPUs and other basically distributed computing in general, that's actually why all of a sudden CNNs became much more popular again. Okay, so that's the quick call out, and so that's why that's why we're doing a TensorFlow session here.
Yep.
So.
Cool. like deep neural networks can have this nice feature that you don't have to really do any feature engineering, right? So you can literally feed anything into your neural network, and you don't have to worry about scaling your data. You don't have to worry too much about transforming that or taking log transform in order to fit it better to your problem, or doing a PCA in order to reduce the dimensions. These types of networks would actually do that behind the scenes. They will learn what to extract from your data in order to separate the signal from the noise. So this is I think the main call-out for this slide.
Yes. Yeah.
And in practice, it means that if you want to predict, we will actually choose the right tools to do the right job, right? So we'll choose, okay, if I'm after a high-end restaurant, potential features might be, location, cuisine, and then whether it takes reservations. Versus if you are after a specialty restaurant, you'd be more concerned about, the vibe and all this stuff. So you don't have to actually specify that in a model, like in a statistical model. The neural network will actually learn that on its own.
Cool. All right. So right now we've been showing you slides, and we were trying to hide from the math, and we're going to continue hiding from the math. Okay. So instead, Joy, this is our turn now. Okay.
Okay, I'll leave these to go home.
There you go. Oh, great. Let's fix this again. Sorry, guys. We're going to have to get the display. Oh, there we go. Okay. Okay, perfect. All right. So this is a tool called Deep Virtualization Toolbox. Okay. Let me make the. So it's a little hard to see. Okay. But what you have here is basically images, and then these are the different layers. Okay. This is a convolutional network layer. Okay. This is a pooling layer. This is a regularization or normalization layer, convolution layer, so forth, so forth, so forth. Okay, so it's an open source product called Deep Virtualization Toolbox. It's actually built on top of Caffe, not TensorFlow, but it's also cool. So we thought this was a good way to sort of give you the intuition of how images work. Okay, or sorry, how neural networks work. Okay, so I apologize for forgetting my pointer, but basically you'll see that, for example, these two neurons are more, oh, awesome, dude. These two neurons here are actually more, okay, thanks. These two neurons are actually more active for that particular image, okay? And then if we go ahead and go down the network through each layer, okay? It gets interesting. So in terms of, we think when it comes to heads, it's probably this particular neuron, okay? So we don't know. We're just going to go ahead and run some images, and we're going to see what happens, because that's how the neural network sort of figures itself out. So let's go ahead and run a real live one now, okay? So, all right, Joy, now this is where you can, yeah. All right, so you will see me here, okay? And do you see basically this neuron? So this neuron basically is sort of the one that's more associated with the head. We didn't plan it this way. It's just this happens by the fifth convolutional network layer. Basically, it's this head. So go ahead. Come on in, dude. All right. So now he shows up here. OK. So now you see two heads, right? Because in other words, the edges that are associated with faces actually end up showing up in that particular neuron. OK.
Apologies for the big head.
Exactly. We have big heads. All right. So back to here. So give me a second as I try to remember how to do this again. All right, so there we go. So if we run the deconvolution, come on in. All right.
Okay.
Yeah, there we go. See, you can see the edges are coming through the actual, the edges of our face are coming through, no problem at all now, right? So this is the neuron that's actually figuring this stuff out. Okay. Again, we didn't program it this way. It's just this is the way. In this case, Caffe, but it's the same for almost every other deep learning project that's out there. There'll be a set of neurons that'll be more sensitive for a particular thing. In this case, this is faces, okay? So let's get out of this. So, but then, for example, if I was to show you, and at the same time and being, showing my book, okay? Well, you know what? Nothing, right? Nothing shows up there. But what happens, can you hold this? Thanks. All right.
I'm a prop.
He's the prop now, okay? So it looks like it's actually this neuron up here that's actually more active to reading text. So if I was to again go ahead and there you go. See, it's hard to see. Okay, keep your hands still, man. right, you can start seeing the text that's showing up inside the book right through here for that particular neuron, okay? So that particular neuron inside the fifth convolutional network is the one that actually figures out that this is a square edge plus there's text in it so we can identify that's a book, for example, okay? So then we're gonna lean a little bit more on that particular neuron to figure that out, okay? So this is, again, we're not talking about the math, this is just to give you the intuition, the idea of how this stuff works, okay? So as we go through every single layer, there's new data coming in, data popping out, and because of that, basically, it's the neurons itself, right, that actually figures this stuff out, and frankly, we don't know where it's gonna go. We just have to monitor and watch how the neural network itself reacts to it all. Question there? Yes?
I believe that patch is actually a filter, right? Not a single neuron.
I'm sorry, say again? Sorry.
That patch that is activating is actually a filter, right? It's not a single neuron.
Oh, sorry, you're right. It's activating he's correct. So the question was it activating a neuron or was it activating a filter? He's correct. It's activating a filter. My bad on that one. Yes, yes. So, okay. So hopefully that gives you an idea what is going on behind the scenes when it comes to neural networks. We included this particular, the deep visualization toolbox directly within the slides as well, so you guys can download it and try it yourself. The only quick call out is that if it only works on Macs or Ubuntu, so I'll give you the heads up on that one. And if you might have some issues working on a Mac, I actually have a pull request in for Macs for it to work there. So otherwise you have to use the Docker instance, and that's actually sort of weird. So, okay,
Yep.
cool.
I think you're next.
Oh, I'm next?
Yeah,
oh, sweet. Okay, didn't know that. Okay. All right. So, in the slides, we did embed the video. So there's actually Yudinsky, he's the guy who actually created this. He's actually a video that explains all that stuff too. So that's actually embedded. We're obviously not going to show that, but that gives you an idea. Okay. So. No, I thought you were doing that, dude.
Huh?
Yeah.
Okay. Sorry. Okay. Now we are into the TensorFlow. Yes, we work. So. TensorFlow, probably, how many of you have heard about TensorFlow? I'm presuming many. Yes, good. Very quick, an open source library from Google for numerical computations, basically used on neural networks. The way it actually works is you have edges, like it creates a graph, right? So in essence, the whole TensorFlow, it creates a graph where the nodes are the data and the edges are the operations you do on the data. And that's how the whole TensorFlow, the whole graph does the computations behind the scenes. It very quickly gained the popularity. So I think it was released in November 2015, and within a month it was like one of the most forked GitHub ever.
Specifically, within 2 months, it was the most forked big data project in GitHub. Period.
Yeah.
So.
There's a support for GPUs. So as Denny mentioned earlier, this is literally what's coming to what enables building bigger and deeper neural networks right now. Nodes, as I said, nodes represent mathematical operations. And like if you think about a graph, a node would be like an add or multiply. Edges are your data that you actually pass through those edges. Thus, TensorFlow, because the edges are tensors, and then the data flows through those tensors. So in a concept, if T1 is a 2x3 matrix and T2 is the 3x2 matrix, the operation is our tensor. So we get the operation going through the TensorFlow. This is a very, very quick example of how you actually code that in Python using the Python API to TensorFlow. I'm not going to go through exactly what's happening here because we're going to have examples of that in the notebooks. But this is literally what you have to do in order to encode what you've just seen. And then TensorFrames is actually yours.
Cool. All right, you got it. All right, so TensorFrames basically, how many of you guys are familiar with Apache Spark? Okay, cool. So half of you are, so I want to do the poor man's version of explanation of what it is, okay? So the poor man's version is Apache Spark is basically a distributed compute engine, okay? It's very powerful because it puts everything into memory, number one, and number two, it actually has data lineage. So the important aspect when it comes to distributed computing is that when you're processing data, tasks will invariably fail. When you have a large enough system, tasks will fail. In the case of Spark, what it has is it actually has a data lineage, so it can actually rebuild what you had lost, basically. So that way you don't actually have to reprocess all your data from where the task had failed, okay? Why Spark is pretty popular? It's actually because of the fact that the Spark core itself offers you 4 different APIs right now, which is Python, Java, Scala, and R APIs. Okay. In fact, Felix, who was here, he's actually a Spark committer himself on the R side of things and for the GraphFrame side of things. Now, the source of Spark can be any one of these things. So in other words, it is a compute engine, not a storage engine. Okay, that's not its power at all. So from the standpoint of storage, it actually hits all these different things. So a lot of the open source systems that are out there. It also hits obviously Azure, obviously AWS, things of that nature. Okay, so that's what makes Spark pretty powerful. In terms of the components, you can, in addition to Spark Core, where you're basically writing similar to MapReduce functions, you can also run Spark SQL, which basically looks like ANSI SQL. Not quite, but it looks almost like ANSI SQL. So you can run SQL queries against your data. Okay. We also have Spark Streaming, the ability to go ahead and stream a fire hose of events right through the system without any problem whatsoever. Spark is able to handle that. It also has a machine learning library called MLlib, okay? And also has GraphX, which is the GraphFrames, though that's sort of going to be deprecated, so because we have GraphFrames now, so I should remove that. But the call out basically is that for a lot of people that are out there, they've already put their data into Spark, okay? They also want to run deep learning projects, though, because they want to go ahead and get access to the power of deep learning, the access of neural networks directly within the context of Spark. So in other words, if you're not using Spark, if you're just using deep learning, that's awesome. But not just because that's really cool, but also the other reason that it's awesome is because apparently all of your data is already clean and it's exactly the way you want it to be right from the get-go, okay? But if you're actually, like most data scientists, the reality is you have to do a lot of data cleansing. You have to do a lot of ETL. You have to join other data sets. So because you have to do that, a common approach right now these days is actually to use Spark to do it. So TensorFrames is the joining of Spark and TensorFlow together. Okay, that's the quick call out. Okay. Oh, sorry. All right. The reason we created TensorFrames is because, long story short, there is a communication issue. When you go from Spark, okay, it'll go, in order for it to talk to Python, which is what the layer for TensorFlow is, it'll actually have to go through Python pickle, between those two processes before it can actually hit the TensorFlow. In other words, we've slowed down the process massively for no good reason. Okay. So what is TensorFrames? Basically, we actually take the data frame API, incorporate TensorFlow so we can actually have the two talk to each other, so we're not actually pickling anything. We can actually basically have the tungsten binary format from Spark talk directly to TensorFlow. Okay? So it speeds up performance massively. And so what I mean, actually I'll show, you know what, just to skip ahead. You don't have to worry about what I mean, what the kernel density scoring is, but the call out basically was this here. If I was to do a kernel density scoring, if I just did Scala UDFs, okay, this is the performance, but then as I go ahead and include TensorFrames, then now all of a sudden is almost half the, twice the speed, half the duration for it to take it. When I include GPUs, boom, it's even faster. So that's the call out that now I can take my Spark projects and I can go ahead and incorporate TensorFlow into it, or the other way around. I have TensorFlow projects, but I need to do additional processing to the data, so now I can incorporate Apache Spark into it as well. Okay, so that's the quick call out here. Excuse me. So conceptually, this is what TensorFrames is, okay? In the previous set of slides, Tom went ahead and showed you the operations. So that's the TensorFlow computation graph. What TensorFrames is basically the wrapper around it. I can take a data frame, communicate through TensorFrames to the TensorFlow computation graph, and then use TensorFrames to get the output as well, okay? So basically, it is the way for those two systems to talk to each other, okay? Yeah, that's really it. Okay, so, and then the other two concepts, why from a business perspective you want to do it. Basically, like I noted, you can utilize TensorFlow with your data. So in other words, you already have a bunch of data sitting in Spark, that's great, go ahead and now include TensorFlow, party hardy, okay? Another super important aspect is this, parallel training to determine optimal hyperparameters. I'm not going to get into the details of weights and hyperparameters, but the context is that as you go ahead and run deep learning models, you have to actually figure out how to go through a massive amount of data basically to optimize these hyperparameters. And so often you want to do that in parallel. Well, guess what? With TensorFrames, you're able to do that now, or much more easily, I should say, okay? So that's the quick call out on why TensorFrames, okay? All right, did that one. Okay, so from the standpoint of getting ready, basically to run the stuff, here's actually all you have to do in order to be able to run it if you're running from the Apache Spark shell, okay? Basically, just -- packages, TensorFrames, okay? Or we're gonna show you how to do it within Databricks, okay? So in other words, you don't have to copy this down. We actually have slides in there that actually show you how to do this, okay? And let's see. Yeah, we're going to skip through this because this is actually already in the notebook, but I kept these slides in here for the purpose of when you download the slide yourselves, you have a reference in what the stuff is, okay? So let's see, we're going to, okay, perfect. Now, tutorial setup. There we go. Okay, I did actually write the URL. There we go, okay? So this part's the slower part because I want you guys to get set up, and we're going to go ahead and get your, basically make sure you got the Databricks Community Edition up and running, and here's where you're going to go get the notebooks, okay? So any questions before, I think this will be a good time to ask us questions in terms of to get yourself set up. We'll probably spend the next 10 to 15 minutes getting people up and running. Once you're good to go, then we'll dive right into the demos and the notebooks, okay? Yes?
So that cluster, I'm assuming, is running CPUs or GPUs.
I'm sorry, could you say that again? Sorry.
That cluster, I'm assuming, it's running CPU nodes.
Oh, correct. So the question is this running CPUs versus GPUs? And because it's a free edition, absolutely, it's CPUs versus GPUs. Now, if you actually go ahead and have your own box, that's where you can run Anaconda directly on it. By all means, go for it. If you've got GPU access there, by all means, do it. Databricks also itself includes GPUs as well. So right now, for the purpose of this presentation, yeah, we're just using the CPU side of things for now, okay? Yes, question?
So in a distributed system, the data is being chunked and sent to different workers for parallel processing. So when you actually chunk the data, then you may lose some of the edges or some of the shapes because the data is being cut and there's no continuity of the data.
Correct.
Not that reduce the efficiency of the tensor.
So he's brought up a very good question, okay? So if I was to assume that my entire environment was a distributed environment and I was to chunk the data, would I then in fact go ahead and be slicing some of the edges, putting them on the wrong clusters, and ultimately causing issues, okay? That's a very good question. The answer basically is this. For the vast majority of the TensorFlow operations, they actually can be run on a single box. So even the training itself is actually run on a single box. What happens is that because I'm trying to figure out, when I'm training, I'm trying to figure out the parameters, and there could be millions of different parameters. What's happening is I'm actually distributing that. I'm distributing the determination of the hyperparameters. That's actually what I'm doing. So the entire TensorFlow computation actually still exists within the context of that single box. So we're actually not slicing. There are projects which allow us to distribute that actual TensorFlow computation. That's true. But some of those are a lot, best way I can phrase it is work in progress because of precisely what you're talking about. Now, okay, I'm not going to get too deep, but the context at least, internally what they're doing is they're mapping out exactly which edge goes to where. And so that there basically is a separate indexing table that explains to you where the edge is from on one node versus where the edge is on another node and where the vertices are. And by doing, it's basically your classic graph, not TensorFlow graph I'm referring to, I mean your classic graph problem. So there are ways you can do that, but even then, those are only good for specific scenarios. So it hasn't been completely solved yet. Cool. All right. Any questions or any concerns or any trying to get yourself set up on terms of the community edition? Oh.
How do you import the notebook?
Oh, sure. Actually, I'm going to show you that now, actually. Yeah, perfect. Okay. So if you guys are already running, actually that literally is the next step here. Import notebooks, okay? So basically these are the steps to import the notebooks and repeat. In other words, run this for all 3 notebooks. Remember, run the download and import the IPython notebooks, not the HTML ones. I mean, actually you can even, if you want to, you can do that, but that's sort of repeat, so you don't need to. Okay? So in order to import it, basically this is what your Community Edition screen is going to look like, okay, like this, okay? I happen to just use shared, but whatever, okay? Just do it wherever you want to do it. Usually I do it under users personally. I just happen to do it shared this time. What you do is that in here, go ahead and right-click on a folder under your name or whatever, or if there's no folder under your name, just right-click, and then you'll be able to go ahead and click on import. If you want to create a folder, just click create to create the folder, but otherwise than that, just go ahead and click on import, okay? That's the first step. Second step is you're going to get a dialog that looks like this. Okay? All right? So basically, instead of choosing file, you're going to choosing URL. Okay? All right? That's the second step. Third step is then, now here's an example of the notebooks. Just go ahead and click on it. All right? Click on this, the notebook. And then that's where you get the URL. So the IPython notebook will show up, okay, and it'll show up in GitHub, okay, it'll look something like this, and then basically get this URL, okay? That's what you're gonna go grab. Once you've done that, paste it back in here, and click on import. And those are the steps for importing a notebook, okay? So I'm gonna go back to here, okay, as a reminder. If you have issues, number one, ask us questions. Number two, the other trick to this also is if you download the PowerPoint itself actually has these slides embedded right in there, so you can go use it. Okay? Cool?
Okay.
All right. Any questions? You import all 3 notebooks, by the way, please. But any questions? Yes?
I don't have the folder shared.
I'm sorry?
I don't have that folder under shared.
Oh, you can create.
Oh no, you can just create a folder. You don't have to.
Yeah,
you don't have. You don't
dump
actually have
it
to.
anyway.
Yeah, it's purely whatever you want. Yeah. Yeah. Yes.
Is there a particular version of Spark we should be running?
Oh, right. I'm sorry. I think I actually mentioned it later, by the way. But just in case you are ahead of us, the version of Spark you're going to run is Spark 2.1 Scala 2.11. Okay. I think I've got it somewhere in the slides, but actually, let's see.
There's in the start cluster, I think.
Oh yeah, I did. Wow. Cool. There we go. Okay. So yeah. So if you're already ahead, then this is where you're going to go. Okay. When you create the cluster, basically what you want to do is the runtime version is Spark 2.1 Scala 2.11. Okay. That's the version you want to have. Okay. There's an option to do the GPU one, but as soon as you do that, they'll ask you to pay. So let's not do that. Okay. So, all right. So once you do that, then go create cluster. You can use PyData if you want to. You can call it something else. Completely cool either way.
You're not able to log in.
Or to set up a user account.
Oh, okay.
So far, so good, everybody? Any other questions?
That's weird. Okay, now you put the working on. Okay, so now it will. So go back to that one and try this dot. Just don't type everything. There you go, and you select that one. Yeah.
Okay. Sorry?
Both 2.1.
No, Scala will be 2.11 actually. Yeah. Because you got 2.10 for Scala, you actually want the 2.11
They're
version.
actually asking you for your working now. So maybe with the dot near signs. And this is still showing up. Can you click on that one?
It takes about 3 minutes.
Yeah. Interesting.
Oh, so isn't that correct? I guess maybe we're overloading it right now. So what you do, in case you are hitting that issue, which is, I've seen that happen before, what you do is you change your availability zone. Right now it's set to US West 2C, just change it to 2B or 2A. So, and you'll be able to spin it up.
Oh, it's because everyone's using PyData as an
Oh, yes. Don't use PyData. I was using that as an example. Yeah, you might be all running over each other at this point with that name. So. Okay, raise the hands on who's ready to go to next. So I just want to get an idea. Okay, all right, no problem. We'll wait then. That's correct, Scala 2.11, not Scala 2.10, 2.11, because the libraries we're about to install are specific to Scala 2.11. Yeah, so, yeah. Yes? Oh, that means you're just waiting for the cluster to spin up, I'm assuming. Let me take a look. Yeah. No, it's okay. It takes about 3 minutes. Okay. Yeah. So. Yes. Oh, just a second. Could you say that again, please?
Oh, I just connected. I've been waiting for 5 minutes. Yeah. It wouldn't connect to a community, now it's connected.
Oh, okay, that's weird. Okay.
I have to create a cluster saying that the size is 10 megabytes of 6.
Oh, it should be 6 megabytes is the default. Yeah.
Am I choosing the right option?
You're going to want to choose Scala, this one, Spark
Yeah, that's the
2.1.
one I tried.
workspace?
Is there anything else?
Oh,
I
no,
need to change
so just change the name. It's actually warning you that the name exists. So,
Alright.
yeah, so just change it to the new name, that's all. Yeah, yes, please. Correct, because you chose GPU.
Oh, okay.
So they're not going to give that away for free. Yeah. So reminder, do not click on the GPU one. That'll ask you for money. So I'm not trying to actually make you guys pay money here, okay? The free one's the CPU one. So again, Spark 2.1, Scala 2.11. It's going to look like this. In other words, Spark 2.1, auto-updating, Scala 2.11. Do not hit the GPU one unless you want to volunteer money, okay? So, I mean, you're more than welcome to if you want, but that's not what we're here for. So, okay. Cool, how are we doing, everybody? Raise the hands on who's got your cluster up and running. Okay. Cool, I guess close enough. All right, cool. So now we're going to install libraries. For those of you who haven't got it set up, no worries. Like I said, download the slides. The slides are there to explain how the steps work. Now we're going to install the libraries. These are the two things you're going to install to get yourself up and running to run these notebooks, okay? The first one is you're going to create a library. So basically, if you were to, this is just me going to my own directory, okay? You go click on PyData, click on Create, and click on Library. Okay, you see that, guys? So go to whatever folder, it doesn't matter, just make sure you know where it is, okay? But click on Create, click on Library, okay? That's the first step. Second step is that we're going to install TensorFlow, and we're going to install it via PyPy, okay? That's all we're going to do, okay? So basically, literally, in this dialog of new library, you're going to make sure the language says upload Python egg or PyPy, and then when under install PyPackage, literally all you're doing is typing the name TensorFlow here, okay? And then click on install library.
Go back to the last slide.
Oh, sure. That last slide's like this. Okay, it'll be under, just right click on anywhere inside your area, inside your full workspace, click on create, click on library. That's how you do it, okay?
Library name?
So the library name is this one. Basically said, this is where you go ahead and choose upload Python egg or PyPy, and you're going to type in TensorFlow. Okay? So far so good, guys? Okay, I'll leave it here. So. Sure, what's up?
Do you need to specify the company's address, email address? Because we actually were able to.
No, you just put in anything there.
Yeah.
You don't have to. Yeah. Yeah.
The problem. So
Sorry?
I don't know why that happens.
I'm not sure either. Oh, wait. Oh, is this Chrome? Yeah, it's Chrome.
Yeah, it is Chrome. We tried in Safari and it was maybe because of that.
You know what I did? That took me for a loop. There's actually a button. You do a go back. I don't know why. If you go back, oh no, go for it. I don't know why. Actually, hit the robot. You have to hit the robot. That one there, and then make sure that other stuff is like. Then you can sign up. Did it hit?
But we had, we had all of them.
Okay, sorry.
Huh.
I don't know. It took me a while. I don't know. I can't explain why.
Okay, so for the rest of you guys, that's the PyPy portion of it, okay? And then basically what will happen is that when you attach TensorFlow to your cluster, it's going to look like this, okay? All right, so it may actually say automatically, attach automatically to all clusters. That's perfectly fine. There's nothing wrong with that. I just happen to have it without it. But basically, you're just going to go ahead and attach it. That's it, okay? All right? And then the second step will be Now you're going to install TensorFrames. Okay, and again, these are the instructions. In this case, you're going to go new library, okay, and you're going to go Maven coordinate. All right, and then when you choose Maven coordinate, go search Spark packages in Maven Central. Okay, all right, so basically Maven coordinate, search. Okay. Yes. Oh, it's create new library as well. So you're creating a second library now. Yes. Yeah. Okay. All right. All right. And then once you do that, you're going to basically in this dialog type TensorFrames. Now, heads up. Sometimes this search is a little hinky. So what you might need to do is flip search Spark packages to Maven, back to Spark packages. But basically, once you type in TensorFrames, it should show up like this, okay? And the one you're going to choose is the 2.8 S2.11, okay? Remember how I was very specific on you need to install a Scala 2.11 Spark cluster? That's because we're going to use the Scala 2.11 TensorFrames, okay? All right, that's what we're going to use. It means also because TensorFlow itself actually had some interesting dependencies, so that's why we're sticking to Scala 2.11 right now. Okay. Sure. Right here.
You probably need to use Chrome instead of Edge or Safari because that's a risky business.
I completely forgot, yes. Oh, sorry. Tom brought up a really good point. If you're using Edge, try not to do that. You might want to use Chrome. Yeah, sorry. I should have said that right in the beginning. My apologies. So, yeah, Edge has some...
Safari has problems too, so if
you're
running into problems using Safari, try switching to Chrome.
Yeah, sorry.
We've tried.
Yeah, and actually this is not specific to Databricks. This is almost every single notebook service has a version of this problem. And basically we consistently find Chrome is the one that actually works. So you're going through a lot of steps right now. It's sort of irritating. So like I said, it sort of sucks, but what's good is that once you've got that done, it's all installed. And then from this point onwards, you're going to be able to use the notebooks, and we're just going to fly through the notebooks portion of this, okay? So yeah, so this part's a little boring. Sorry about that. But that's what it's going to look like, okay? Let's see, we got that. You're going to use so the question is which version of TensorFrames. The version you're going to use is 0.2.8-S_2_11. Okay, the 2.11 represents the Scala version. Okay, so that's 2.11. Okay, make sure you get the one from Databricks, not from Tim Hunter directly. Okay. It's okay, actually, it might even still work, but Tim is no longer maintaining his own version of this, so it's actually under the Databricks library now. So, okay? You're next. You're next. Huh? Give her your one. Yeah. Okay, cool. Cool. All right, so once these steps are done, it'll look like this, okay? It'll add all this fun stuff, okay? Again, if it says automatically attached, that's perfectly fine. There's nothing wrong with that. If you want to turn it off, that's fine too. Just make sure it is attached to your cluster. That's all I'm asking, okay? And then, boom, that's it for Let's Go. So I'll go back to the other screen just in case you need it. But basically, that's it. Those are the two things you needed to do from the library perspective. And if you've already imported the notebooks, then you're set. We are good, okay? Any questions? How are you guys doing on this stuff? Cool? Raise your hands on who's good. Perfect. All right. I think we're ready to start. Like I said, for anybody else who's missing it, you can probably ping us off the side and or download the slides. Like I said, the slides themselves actually have screenshots for all this stuff. Okay? All right. Let's rock it now. Joy. Sorry?
I'll explain the softmax, but do you want to go through the first part?
No. It's okay. Nah, just run it here. You're fine. Here, do you want me to clear the results, or do you want me to clear the results, or just run it cell by cell?
Just run it cell by cell, and I'll explain the softmax.
Okay. Oh, do you want me to run it? Oh, you can do it.
No, you can do it.
Okay, fine. Okay. All right, cool. All right, so we are on this particular notebook, okay? So basically this notebook's, generally we like doing a lot of our demos in these notebooks because even though you went through a little bit of hell and high water on this stuff to get it installed, it actually allows you to include visualizations, include Markdown, things like that. It makes it a lot easier for you guys. You guys are, I'm sure you're familiar with Jupyter Notebooks. This is a very similar concept, okay? So basically, the first part of the notebook basically reminds you of the cluster setup. So everything you just went through basically was that, okay? That was the first thing. And then now we're gonna start MNIST for ML beginners. So for any of you guys who are just beginners on this stuff, cool. So we are talking about looking at handwritten digits, okay? So the handwritten digits is based off of the NIST Special Database 3, which was actually off of Special Database 19. I don't know why I know that, I just do, okay? So what you have is basically census and high school information that made up what you see is here 28 by 28 pixel images, 5041, okay, as an example, okay? So this is what it looks like. The process is to digitize that data. It becomes an array for you to go ahead and start hitting, okay? So I'm gonna show you exactly what I mean by that. All right, so first thing we are gonna do is this first cell. So if you're under import the data set, you see this command here, import MNIST digits images data from TensorFlow, blah, blah, blah. Basically, TensorFlow itself already includes this data set directly. I don't have to import anything new. So all you gotta do is run this, all right? Oh, sorry. And how do you run it, you ask? Okay, so for those folks who are not as familiar with Jupyter Notebooks, you've got two choices. Either you can click on the cell, and then you can click on this play button on the right here. Oh, sorry. On the right here, okay, the little play button. For those of you who don't want to hit such a small little play button, just Shift Enter. So click on the cell, click Shift Enter, and that'll run the cell for you, okay? All right, so that's what's going on here. That's the first step. So what is this image, okay? Like I said, we've got ourselves a 28 pixel by 28 pixel image with a size of 784, okay? That's what it looks like, okay? So for example, if I was to run this, specifically this MNIST train image, I want to get image 25138, okay? That's specifically this image, all right? When I look at the label for 25138, which is this one, basically it indicates to me, for those who are all fun on one-hot encoding, it's the 1 is on the 9th spot, so it's for the number 9, okay? So that's the label. That tells me what is the number for this particular image, okay? The image itself is actually here, okay? So, wow, this looks really weird, right? Right, but mainly because it's not a 28 by 28. So if I actually scroll this image, here's the numbers. So this is the digital representation of the number of one of the handwritten 9s. Okay, that's what this is, okay? In fact, what I did is I actually included, oops, sorry, this. So this tells you how anal I got. Basically, you'll notice 28 pixels this way, 28 pixels this way. This is Excel. I took every single number, got it in there. If you zoom in on the numbers, you'll see the 0.19 whatever, all those actual numbers, okay? So actually there's a high def version of this image somewhere. Let me see if I can find it. Oh, here we go. All right. You guys want to know the suffering I did for this one? Here we go. All right, so here you go. So you see right here, 0.18 represents this shading, 0.61 represents this shading, 0.69 represents this shading, okay? So that's how this handwritten digit is represented, okay? So it's actually all here. Again, the notebook has it. It links to the image. You can actually even look at this image if you want to suffer for some reason, okay? It is not a fun thing to do because I had to export the data out and then remap it and then just, you know, and I had to use Excel, which is, yeah. God. So, all right, so, but that gives you an idea. That's what the digital representation of the number looks like, okay? That's how it's stored, that's how you're looking at it, okay? So now we're gonna wanna predict, okay? So we're gonna go ahead and talk about, okay, this is actually the part where Joy's gonna talk about because she's much smarter than I am. But the context basically is that we're gonna be using softmax regression to actually figure this out. Go for it. Oh, you don't need this. Actually, you can use the pointer if you wanna use the pointer. Yeah. Oh, the red light here for the pointer. Yeah.
So, I think for most of the people that are familiar with deep neural net, you probably already know and familiar with softmax already, which is often applied at the last layer of a deep neural net. But for this beginner tutorial, we are not using any deep neural net yet, i.e. we are not really using multiple layers of convolutional layers yet. We are just using one single classifier for this beginner tutorial. So basically, all of the input that Denny just showed that composed that number, we're just gonna sort of stretch it into a single I think 3-dimensional array, which we call tensor here, and then we're just gonna feed this whole big number of arrays into a classifier. In this case, is the softmax classifier. It is a generalization of the logistic regression. So if you're familiar with logistic regression, this is really sort of just a multinomial, a multi-class logistic regression, because we have actually 10 classes here, right? From 0 to 9, we have actually, instead of a yes, no, 1, 0 answer, we have 10 possible answers or categories that we are trying to put the input number into. So to visualize how, or to get a better idea of how this works, so here's the an illustration of how the math works. So basically, you have a set of inputs, and for the sake of simple illustration here, we're just stretching. For example, if I feed an image of cat into the array for x, which is the input we're getting here. So we're just stretching all the pixels into a single column here. And to train this classifier, we have actually a bunch of weights here, and then we have a bias. These are all the parameters, or the coefficients for our linear classifier here. So basically what we do is we dot product w times x plus b. That is basically our function, which is basically what our model does. And we produce a score, which is a sort of a class score of the probability that our this function just gives to the 3 potential categories, like cat, dog, and car. And what softmax function does is it basically exponentiates the score and then normalize it to give you this probability with better intuition. So basically, we take that raw score out of the linear function that we've just got those raw score, and we exponentiate the score into this form. So we get the sort of the unnormalized probabilities, and then we normalize them to get the probabilities. And when you see here, so you see the cat actually got a really low probability of only 0.016, which means this model, basically the performance right now is really low. It's giving cat this really low probability, which means it definitely needs more training, where it gives actually dog a much higher probability, which means, yeah, this is the output score. The output is actually wrong now, and the loss function is the log of the probabilities. So you get the lower score you get for the correct output, the higher the loss is, which means you're losing a lot. This model is not working out for you. And but when you give the correct output a really high probability, then you get nearly 0 loss, which means your model is working right now. So that's how we do the whole cost optimization based on this loss function. So that's how softmax works.
Thanks, Joy. And so for more information, we actually put some links inside here. And actually inside the slides, we actually have some good links to other course material that if you want to dig into it, just because we didn't want to get too deep into the math behind loss functions and weights. Okay, so this is a quick call out. So the implementation for this is this cell right here. And actually, you'll notice it actually happens really quickly here, okay? So basically, you've got a placeholder, you put in the variables for the size of 784 to 10, and basically, you're just simply implementing the softmax regression, which is literally just this line, okay? So pretty sweet, okay? And from the standpoint of TensorFlow, it's really fast. You got softmax regression. You can train the model. That's what this basically bit of code base is. Most important aspect is here. Basically, you're basically batch training the system, okay? And then once you're good to go on that front, we will evaluate the model. So basically, all I mean evaluating the model is more like, we already know what the actual value is, and but we're gonna see how well this particular softmax regression predicts the numbers. So in other words, for the MNIST data, we already know what the labels are. We already know for each image what the number is actually supposed to be. So now we're going to see how well it can predict, okay? And in the case of this, hey, it actually predicts at 91%, okay? So it's not bad. It's not great, but it's not bad. And it actually also happened pretty fast. 0.04 seconds on a 6 gigabyte 0.8 core node. Okay, so and this is CPU, not GPU. Actually, not even 0.8. It's more like 0.67 or something like that. Okay, so basically, it's screaming through this pretty fast. Now, it's only MNIST data, so it's not a lot. For the purpose of this tutorial, that's actually why we're doing MNIST, because you guys can run it. In the next section, we in fact actually had to reduce the amount of test data we had to run because we were obliterating the size of the cluster, okay? Because it's only 6 gigabytes of memory and 0.67 core, okay? So you actually have a lot larger data, get yourself a real cluster or a real box or even one core, and then you can probably finish it, so. All right, cool. Did you want to do the? Yeah. Cool, all right, go for it. Oh, sorry, no, not this one. Sorry. I'll do that one later. Okay, so Joy's going to jump into the softmax regression from this standpoint. Let me switch to softmax and start repeated update. There we go. But the quick call out is basically this is from Joy and myself. Well, actually, all three of us were pretty big fans of Andrew Karpathy's course. Okay, so that's CS231N. If you guys want to dig into the math behind this stuff, it's all available on YouTube. We've linked it in the slides. Okay, but if you want to dig into it, by all means, go ahead and watch the course. It's on YouTube. It's for free. The slides are available for free. It digs into the math behind all this stuff, so you can really understand not just the intuition, but also actually how it works. And here's one of his many JavaScript demos. Yes. Sorry.
So this is meant to give you, like now we've gone through the math a little bit, and this is really intended to give you more intuition behind the math. What is this softmax trying to do, or what is this linear classifier trying to do from an intuitive standpoint? So what you see here, this demo on the left, so basically we have some dots here, red dots, green dots, blue dots. Each dot basically has is a two-dimensional sort of data point. As you can see, that's why in reality you can have a lot more dimension for your input, but for the sake of simplicity of this demo, we are just using a two-dimensional data points here, so we can easily visualize it on a flat plane like this. So each dot obviously has a value on the x-axis and y-axis. That's how we plot these dots on the plane here. And we have three different categories for these dots. Basically, that's the red category, the green category, and the blue category. And that's what we're trying to classify these dots into. We're trying to classify them into three different categories: the red, the oh, okay. The red, the green, and the blue. So let me just. So as you see, if I try to change any of the weight here, so for example, these these weight points, these coefficients actually are the classifier for the blue dots. So if I move this up and down, you can see actually it really, I can change the spatial boundary for this blue classifier for where it should be really putting the blue dots into the blue category here. And this bias is actually, it can affect my position as well. And now I'm manually manipulating the position, but behind the scene, if I'm trying to train this, that's what the algorithm is trying to do, is basically literally trying to move all these classifier, all these straight line boundaries around to try to find a boundary in a spatial space that would separate all these dots into the category that they belong to. That's what intuitively it's trying to do. So if I randomize, the parameters, you can see now it's not really getting anywhere, but then I try to. So every time I randomize, as long as the classifier is running, it will always try to go back and find the proper boundary of separating all these three categories of dots spatially into three different spaces. So that's what it's trying to do.
Cool.
Yeah.
Thanks, Joy. And yeah, for you guys who are, Thanks. For you guys who are like math folks. Okay. Math book, there we go. Yeah, basically what it comes down to, this particular JavaScript demo, what you're trying to do is basically you're trying to knock down that loss function to as low as you possibly can, because that means you're actually going to go ahead and get it as close to zero as you possibly can. So that means it's actually classifying the data correctly. That's what it boils down to, right? So when we keep on talking about things like weights and hyperparameters, basically this is you, well, in a JavaScript console, manually manipulating this stuff. That's actually all that's going on here. So it just gives you some context on how a linear classifier, how softmax regression basically works in this context, okay? But this is the starting point, okay? So now that we've talked about softmax regression, remember we said that the precision for the MNIST data was 91%. We know for a fact that that number could go significantly higher than 91%. 91% is actually too low. So that's where convolutional neural networks comes in. Okay, so in other words, let's do better than this, because up to this point, it's basically been SVMs, maybe softmax regression, but we actually have not been able to get more precise. CNNs allow us to get more precise now. Okay, so slider.
Slider or notebook?
Notebook?
Yeah, I think we did with notebook.
Okay. Do you want to explain the sections?
Yeah.
Okay. All right. Is this one?
Yeah.
Oh, okay, cool.
This is one, right?
Oh, yeah, just this one.
Yep.
Oh, let me run it. You can explain. I'll start running it.
Okay. So right now we're going to be showing you literally how we build a convolutional neural network with TensorFlow. This is still a single-threaded execution. Denny will later walk you through how you can do it in a TensorFrames setup. But right now we're just going to jump in and create the network that will help us to literally recognize the digits, right? So there are we've created four helper functions, right? So the first one, when you see the conv2D, is actually creating a 2D convolution. So just to show off hands, guys, how many of you are familiar with how the convolution works? Okay, all right. So just a quick, our x over there, this is our input data. The W there stands for the size of the convolution, right? So this is our filter. This is the, how many pixels by pixel, we look at the same time, and we apply, to our image in order to, calculate the convolution from that. So that normally will be some odd number. So it will be either 3 by 3, 5 by 5. This is our kernel, right? we've wrapped this. So this is actual call to the TensorFlow, where we go TensorFlow neural network convolution 2D. This is just literally a wrapper function around that, so we don't have to specify all the times the strides. Strides here, what it means, actually how many pixels you offset when you move loop through your whole image, right? So we move 1 pixel at a time in order to create our filtered image. So in this case, we will move 1 left, 1 right. So actually the middle ones, they specify 1 pixel at a time right and 1 pixel at a time low. So go lower.
Actually, do you want me to just show that?
Yeah, that would be
okay, so
good.
what Tom's talking about here basically is this. So again, we actually incorporated this within the deck, so you guys can basically play with it. Where the heck did I put it though? No, that's not it.
Oh, there you go.
Where?
Here.
Oh, cool. Sorry. Yes.
Yep.
All right. So if remember he's talking about strides and basically moving pixels. So if this top left, okay, or these represent the number, okay, that you're trying to read, okay, and the little squares you've got there are pixels. Now again, this is from Andrew Comparthy. We're not that smart, okay. Then basically this is the movement of flow that's happening to read the pixels, okay, inside your data. So you're not actually looking only 1 pixel at a time. You're actually looking at a bunch of pixels all at once, okay? 3 by 3, 5 by 5, in that nature, okay?
And then it actually goes down and drills down. In this case, this is a 3 by 3. The whole image is 7 by 7, if I read correctly.
Yeah, I think so.
And it's the stride it moves 2 pixels at a time right and 2 pixels at a time low, right? So we start from the top and then we move to the next one and yet the next one, right? So we skip 2, and then once we reach the end of the image, we skip another two rows. That's how you can actually see over here, it highlights when we move to the middle one. It actually highlights which one we are outputting from this convolution. Does that make sense? So far, so good?
Okay, cool.
All right, so I think we can switch back to the notebook. Cool. So in this case, we are actually not skipping 2. We are moving 1 by 1. So we read 1 column, we skip 1 column at a time and 1 row at a time. The padding, the final parameter, the padding, is actually when you think about the convolution and the way it was shown actually on the slide, is that if you had a 28 by 28 pixels image and you specified a 5 by 5 convolution kernel, the resulting image would be 24 by 24. And that's simply the way the convolution works, because it will cut off 2 rows from the top, 2 rows from the bottom, if you have a 5 by 5, and then 2 rows from the 2 columns from the left and 2 columns from the left, from the right, resulting to in a 24 by 24 resulting image, resulting feature. TensorFlow is actually padding some of those 2 rows, 2 columns on each side. So that's why whatever comes out from the convolution in TensorFlow, when you specify the same parameter, will also, if we feed 28 by 28 image, we'll get 28 by 28 feature out. The max pool, this is once again, this is our wrapper around this function. So this is our input, and then we specify the kernel size. We specify the kernel size 2 by 2. What the pooling layer does is actually looking the 2 by 2 portion of the feature, and it averages the values that it sees in that particular window. So let's say if we had 1, 2, 3, and 4, the resulting output from that particular pooling would be, if my memory.
What you said 1, 2, 3, 4.
1, 2, 3, 4,
yeah,
right?
Yeah.
So, yeah.
Yeah.
And then we specify. So unlike with the convolution, here we skip 2 and 2, right? So if we specify a kernel 2 by 2, then we don't look at these pixels anymore. We move to the next one 2 by 2, right? And then next one 2 by 2. And then same thing when we go lower, we don't read these pixels anymore. We move to the next 3 and 4, rows 3 and 4. Does that make sense? Cool. The weight variable, this is essentially the way we initialize the weights. So as we were talking about the neural networks and how we build them, the way once we decided on the structure of the neural network, we need to actually specify some starting parameters of the of the weights that connect all of these neurons. Just like with the statistical model, you have some starting parameters when you, let's say, estimate a multinomial logistic regression, right? Normally, they are hidden from you because they are normally assumed 0, and then the algorithm takes it from there. Over here, we could have set it up to 0, but then we would get nothing at the output. So we initialize that to something drawn from a normal truncated distribution, so it's never going to go below 0, and with a standard deviation of 0.1. So we use a variable because that's going to be changing. As we train our network, this is going to be a changing value over there. And then this is what the call to this particular function returns. And then the bias variable is literally very, specified in a very similar fashion. But instead of drawing from a distribution, we just specify that to a constant. In this case, this is 0.1. The shape, if we say, okay, give me 784 by 1, it will return 784 values, single list. If we specify 3 by 3, it will give us 9 values stacked into 3 by 3 matrix. And then the final one, we get the variable out.
Cool.
Okay.
All right. So yeah, let's talk about the model. Then we'll do a shift to the demo. So
okay.
Yeah. So. Yeah, go ahead. Sorry. No,
you want to
No, go for it. Go.
Okay. So in the input, as I said, each image in the MNIST dataset has been transcoded to 28 by 28. I think originally they were more than that.
Correct. Yes.
But for the purpose of this exercise, and then in TensorFlow, we're working with the 28 by 28 representations of those handwritten digits. These get pulled through a first convolutional layer. So this convolutional layer has a kernel of 5 by 5, right? So we're looking at 25 pixels at a time, and then we literally skip one row, one column at a time. So the resulting, as I told you, because we've used the padding equals same, the resulting feature size is also 28 by 28, right? So that's the first convolutional layer. There's 32 features in this particular one. What do they do? So the convolution essentially allows you to, Denny was showing you the demo when it was recognizing the edges, or was kind of, starts to recognize which feature is tied to a face. In this case, what it actually does, we're training the kernel. So we're training the weights that are associated with the kernel, and that results in either we invert the image, or it actually increases the contrast, or it actually inverts the image. So that's how the image representations within those 32 features here, this is how it works.
So just to add some point, and when we're showing this, now this isn't TensorFlow, this is actually using Caffe, if I recall correctly, okay? But the call out basically is that this should give you some context that the first is your input, okay? So forget about the sizes, because what TensorFlow does is different than the way this particular implementation is. But if you go ahead and look, this is the written digit right here, okay? That's what it goes. When you run the first convolutional network, this is what the number is going to look like. Now in this case, there's only eight of them, okay? And in fact, there are actually 32 features in the case of what we're doing. But the idea is that this is what's going to start looking at. So basically, it's building up, that's what the layers are actually doing. So this is what the number more or less looks like after the first convolutional network, okay?
And they all will be different.
Yes.
And there's, as I was saying, some of them will increase the contrast, some of them will help later on, the later stage, to detect the edges and so on and so forth, or different distinct features of the digits that you're actually trying to recognize.
Back to notebook?
Yep.
Cool.
So the pooling layer, as I was explaining that, it will actually go and then shrink the image, right? So we look at 2 by 2. We're using 2 by 2 kernels here. It will actually shrink the image to a 14 by 14, and this is because we're using strides of 2 by 2, so we never look at the same pixels ever again. What it does, it actually averages the number from 4 pixels. It will actually shrink that to 1.
Yep. So just to add to that, so basically here's the pooling layer. So you're not seeing much of a difference between the two, but basically if you go ahead and look at this is actually after the first convolutional and the activation function, ReLU activation function. Basically, there's no difference between this layer and this layer, except for the fact that in this case, it's 24 to 12, 12, okay? So in other words, our numbers are different for TensorFlow, but basically, it's just basically half the size. That's what it boils down to, okay? So we've taken that image that we have here, and now we're shrinking it down.
Yeah.
Okay? That's what the pooling layer does, okay?
Correct.
Yeah.
Thanks.
That's what?
Right, so if you can stop for back to the
Yep.
one, I want to talk a little bit about the ReLU.
Oh, sure.
Right, the activation function, right?
You want to go here, or you want to get the notebook?
Yeah, so this is good. This
Perfect.
is good.
Okay.
Yeah. So as you can see, if you remember the slide with the activation functions that I showed you, we had the ReLU, which is outputting anything. As you can see, the difference between this and this is literally like we only output whatever the input to the neurons is, or to this layer is, only if it's greater than 0, right? So that's why you see lots of...
Sorry, I'm going to pause it so you can actually see the difference. There you
go. That's why you see lots of dark things, and only those highlighted pixels get showed up, right? They only show up here. So there's a number of reasons why we use this. Different implementations, like Denny and I, we did the also a MNIST workshop a while back where we used different framework. We used a hyperbolic tangent, and it works fine. The problem is with the hyperbolic tangent, when we train the network and we go beyond, if the sum of all the inputs getting into the neuron exceeds around, I think 2, the function becomes literally flat because it peaks at 1, and then any subsequent training to that neuron is literally out of the question because the derivative in that point becomes 0. Because it flattens, and then we cannot train that neuron anymore. So it essentially becomes dead from the purpose of using this network. ReLUs do not suffer from that, right? So it is a simply, constantly rising or falling function, right? Yep. Depending on, on the weight or how it's trained, but it's constantly, it cannot ever reach a 0 derivative, so it never becomes dead. That's why they kind of really state of the art right now, and also very helpful in, not making our neural network dead. Okay.
Cool.
Right. Thanks.
That's that. Back to the notebook. Here we go.
Okay. So right now we are at the 14 by 14. Right now what we do is we create another convolutional neural network, or convolutional layer right here. So right now we're going from 32 features, and we are actually expanding that to 64 using exactly the same parameters. So we use 5 by 5 kernels. So we loop again through this 14 by 14 right now, 14 by 14 image, in order to create another 64 representations of the same image that is already a little bit shrunk down. And with this, we'll be detecting distinct features of the handwritten digit. A second pooling shrinks that image even further to 7 by 7 representation. A call out here is that TensorFlow, if at this point we would end up with let's say something like 6.5 by 6.5 by the way the math works, it would actually pad that to be 7 by 7. So if there is an unequal or some odd number coming, a float coming from the pooling layer, it will actually be padded to something that is an integer. And then finally, at the very end, we actually take all of these 3,000, close to 3,100, a little bit over 3,100 neurons from this particular layer, and we squash them down using a fully connected feed-forward network. What I mean by that is that if you look at all of those 64 7x7 features, all of those 7x7 features would be connecting to a 1024 single layer line of neurons, right? So we take 64 or 3,000, 3,100, and then we actually literally connect them to a layer of 1,024 neurons. This reduces our feature space, and it further allows us to train the network better. And then in the final stage, just like Joy was explaining the softmax, we use the argmax here to actually squash it back to, okay, we want to know whether it's 0 or 9 or 3 or 10. So we use argmax. So whatever we get from squashing from 10,024 to 10, we then select the winner, or we can call it winner takes all kind of thing. So whichever gets activated with the highest value, we say, okay, this is the digit we want to assign it to our target. So that's the output from our network.
Cool. So just to give you some additional context to everything we just told you, because literally we just told you the code, okay, on how this works, okay. In fact, the code is right here. Okay, that's it. It's one cell. Everything we just displayed is one cell. That's it. Okay. So to provide some quick context, again, we've included these links to these demos already in here. So like I said before, here's what the number looks like input, right? And then even though the numbers aren't the same, it should give you some context between what the input was, convolutional layer, activation, pooling, convolution. And remember, in the end, when you're building these neural networks, that's all you're doing. Okay, all you're doing is basically adding convolutional networks, pooling, maybe regularization, convolutional network regularization, and then basically fully connected. That's really all that's happening, just adding tons of layers to this. And so, yeah, if you scroll down, and so basically you look at this, right, in this case it's using softmax, but basically it's predicting it's 0, right? That's what it's doing right here. And so this is the example predictions for the test set that it's been running on JavaScript. Sorry. So for example, here are all the different numbers, and it's how well it's predicting. So they predict it's a 9. So vast majority of the neurons are indicating, yeah, this is a 9. That's what it thinks. These are zeros. So overall, basically, as time progresses, the network is actually doing a really good job figuring out what these numbers really are. Okay.
Or in other words, minimizing that loss function that we've specified. In this case, it's. I think it's also, yeah.
Exactly. So here's exactly that representation of the loss function right here. Okay. Initially, as it starts off, it's higher, but over time, as it's learning more and more information, it's actually dropping down, dropping down, dropping down. Okay. So that's the context of that. The other way of looking at this, by the way, if you ever are able to go ahead and get the tool up and running, and you're more than welcome to go ahead and ping me if you have questions on how to get this tool up and running, because like I said, I've got actually a pull request to get it to work. The context is that if you look at, for example, this convolutional network layer, using the visualization tool, right, this is what the pooling layer looks like, okay? So this is what the normalization or regularization layer looks like. This is now another convolutional layer. Pooling layer. So you notice that, for example, when I go from the first layer, right, I have much larger pixels. When I get to the second layer after I've pooled it, I've got smaller, more pixels. That's back to the same idea of higher number. Basically, I'm pulling it down. So in other words, and I'm doubling the size of doubling the number of features for me to work with. Okay. So this is basically that exact same context all throughout. And just like we were demoing our faces in terms of looking for the edges, basically this will sort of give you the intuition of sort of understanding how the network is working throughout to sort of calculate or understand how to identify those the numbers, or in this case, pictures or images or us, that type of thing. Okay.
Or books.
Sorry?
Or books.
Or books. Yes. And one final note before we actually just show you how it happens. We didn't go through this in the slides, but they're available here for you. Again, to help explain the concept, we actually went ahead and actually extracted like the number 9 and what it looked like. And so for each layer of the convolutional network, we actually sort of explain, well, here's the code, here's what happens, here's what the numbers look like. So that way you can take your time to basically review all this stuff, because we knew we just threw a lot of stuff at you guys right now. And so hopefully the slides will help you sort of digest what we just threw at you, okay? But basically that one cell of code is all of this, okay? So again, these slides are available for you guys. You can download them and party hardy. That we're good on that one. Okay.
All right.
So you want to run?
Yeah.
Okay, cool. There you go. Actually, we've already
run.
Actually, we already ran.
Right?
Yeah. So you guys can run this, by the way. Just as a quick trick. Sorry.
Yeah.
Yeah. For this notebook, just click on Run All. Okay. You can just run the entire thing. Okay. It'll take a little bit longer to run, by the way, because it'll take a while for the training to finish.
Yep.
And then do me a favor, scroll all the way to the bottom.
This one?
Yeah. Keep going. Yeah. Okay. Yeah. We purposely. Oh no.
I think it's.
Actually, no. Go down more.
More?
Yeah. There you go. Yes. We purposely limited to 500 images, okay, as opposed to all 10,000 test images. Not because we don't want you to run it. Well, actually, we don't want you to run it, but mainly because it's 6 gigabytes, 0.67 cores. If you go beyond 500 images for the test, it'll actually give you an interesting nonsensical error. But basically, that interesting nonsensical error is because it ran out of memory. Okay. So, but basically, if you scroll all the way to the bottom, still. Yep. Thank you. Basically, if you run this yourself on the full, basically now here you go. Here's the training, the test accuracy, 98.95%. Okay, so
which is respectable.
Yeah, pretty good.
For this one.
Now we're feeling a lot more comfortable. So this is the heart of why CNNs are super interesting for us.
Correct.
Okay. Yes. Question.
Is there a theoretical lower limit on the number of images that you need?
For the testing or for the training?
Yeah, for the testing and training.
For the training. 500 should be enough to draw some, we can specify the standard error on that.
Some point below which, like,
But because don't forget, even if you're 500 sounds about right to me. But the problem is that if the data has a lot of variability, then you're hosed from that standpoint, right? So if you've got 500 like images that are somewhat similar, sure, yeah, absolutely. In fact, the MNIST is a perfect one. In fact, I think I only trained on 1500 for the same reason, because I was running out of memory. Okay, so
it depends on how representative your sample is, right? And you can train statistical models with the limited number of features you use on probably, I'm stretching it, probably 300 samples. I wouldn't go that far myself, but you can do it. But there's always this, how well this model would generalize later on, right? So on 1500, we get to this, right? So to 97.5. You can probably go lower and then test it out. We didn't do it for this exercise, how to vary that, but you can actually see, we did that for the 20,000, right? So
yeah, the 20,000 right here.
For the 20,000, it goes up. So it depends how, later on, how would that generalize, and you can definitely calculate an error around that. It's just like, inference from, when you pull people and then you sample 1,000 people, you can always put a bound, like it's plus minus 3%. You can do the same thing in this case. Okay?
Cool. Any other questions, actually?
Yeah.
We're about to switch gears to TensorFrames, so that's more of the Spark side. We'll actually probably finish it in about 10 minutes. So and so if you got questions, by all means ask now. But that way we can also get you guys out early, or if you guys want to ask more questions, that's cool too. So go for it.
So just a question following this line is there any tool in TensorFlow you can help us to determine, do some pure statistic analysis to see if sample are a typical representative of all the situations that you see?
You'd probably have to do it before you feed into TensorFlow. So there are many tools available to you in Python environment. Right, you could use SciPy, you could use scikit-learn. Probably will have also some statistical tests to determine whether your sample is representative and has enough variance to actually train on. So you don't just learn the features in your data set. That's why we always have this, you can see that the training accuracy is 1. So it learned that the network learned perfectly what it was, trained with. It learned perfectly to recognize that. But when you actually fit it with the testing data set that it's never seen, you can still say it generalizes very well. Right?
Yeah, I mean, so just as a quick reminder, like when it comes to testing versus training, remember the whole purpose when you train any ML model, deep learning model, whatever it is, the context without a doubt is that you're going to have a separate set of data for training and a separate set of data for testing. You don't want to intermix those two. Yeah. So the MNIST data is actually a perfect set just because if you're starting off, it already has already
Split.
very split. Here's your training data, here's your test data, and you're good to go, right? But then there's various Python, PySpark, whatever tool you want. There's various tools that you do, random array or whatever else, which basically will take all the data, split it for you, so that way you can say, here's my training data and here's my test data. Now, the one thing to remember is that for folks who actually have a lot less data, this actually was common in healthcare. When you're doing machine learning models for that, you're going to actually split it from training data. You're going to have a cross-validation set to actually, which is basically rehashing the training data to validate the data looks right before you apply it to your test data, just because you don't actually have a lot of data.
Yeah.
Now that I'm going a little outside the bounds, but
I was just about to say, just about to make a point about the cross-validation data sets.
But the context I'm just saying is that, in the case of a lot of these samples that we have, like for example, when it comes to MNIST, that's more than enough, 55,000 training, 10,000 testing. In the case of CFAR, there's enough images for you to do it. If you really want to play with images, go to ImageNet, okay? ImageNet has 15 million images, so you're good to go on that front. But yeah, there will be some scenarios where you ultimately won't have enough of the training data to work with, and so then that will be, now you have to switch from training to training.
Improvise.
Yeah, you have to improvise and start doing cross-validation
on the
data sets. Yeah.
Another useful data set is MS Coco. Is actually from Microsoft. There's a bunch of images which already have boundaries around them, so you can actually train to recognize objects. And there's also captions written about that, so you can build a model that will do an auto captioning. Yeah, there's a question.
Yeah, any guidance on selecting the suitable parameter for a new program?
That's actually the data science job.
It's quite often it's like a trial and error. So the first workshop that we ran, we only used 6 features in the first convolution and then 12 in the second one, and it got to 97.5 accuracy.
Yeah.
With 32 and 64, we got to 97.5. Right, so it's a trade-off. You probably will have to play and trial and error. And does that answer? Help? Not?
So if I wanted to use my own data for this, there's a button on the left that says data, right?
Yep.
Can I just upload like a zip file full of train and test images?
If you have images, then yes. Yeah. There's nothing stopping you as long as they purport to 28 by 28. Right, then if not, then you'll have to change the parameters of the.
I'm just talking about using Databricks.
Oh yeah.
So the quick note is that you can definitely upload your data into there. Typically, you won't upload it as a zip. You'll upload it basically as an unzipped file. But no, you can still do it. I'm just simply saying you just have to write the extra line of code to ungzip it when you look at it. That's all I mean by that. So basically, you can certainly put the images up there. You can certainly run it. I do want to give you the heads up because this thing barely ran. Because again, 6 gigabytes, 0.67 cores. You might want to go ahead and actually run this on your own box or actually get a larger setup, okay, when you're doing it, just as a quick call out. Again, the purposes of this was more like, just make it easy so I didn't actually have to, we all didn't have to go ahead and install various versions of Python and Anaconda or whatever else onto your box, and then this actually would have been a longer, process for us, so. Sure.
Just for the notebook you have, I'm just suggesting that it's good to.
Yeah, so the comment was that we should have set the random seed for reproducibility. Absolutely. So the part of the reason why I didn't do it at the time was mainly because if I ran it enough times, that number actually would have went higher, and I forgot to figure out what the seed was when I did it. So in other words, yes, I was lazy. Yes, let's call a spade a spade. So.
So you haven't used TensorFrames?
Yeah, we're going to that.
Yeah.
Yeah.
But before that, but it is doing good, almost 98%. Why do you need TensorFrame?
So for TensorFrame as a useful, probably not for this one, but if you have a large data set, right? And also if you want to, you do all your data preparation in in Spark environment, then you don't have to leave the whole environment. You don't have to save it to disk, then go outside of Spark and then read it again and run it through TensorFlow and then save that to another file, read it again in the Spark if you wanted to do further work on Spark. So this is kind of like keeping that within the same environment, so you don't have to switch environments in middle. Does that make sense?
Cool.
You want to switch?
Yeah.
Or we have
any other questions? And otherwise, we'll switch to TensorFrames.
Cool.
Okay, cool. So here's the final notebook that we've got here. And again, with TensorFrames. Again, I'm just going to run off just to give you some context. Okay. Basically, we've more or less, in case when we originally designed this, we originally wrote this notebook with the context that we're going to do a lot less TensorFlow and more TensorFrames, and then it became exceedingly apparent that was very silly of us. So we went ahead and rewrote the course. But by the same token, in case you wanted to go to TensorFrames right away because you were already a Spark person, we actually added some additional info directly into the notebook so you can understand the concept of what TensorFlow was. Okay, so we're going to skip all this. Okay, but basically it's just talking about the mathematical operations. And why using placeholders. Okay, that's all the stuff is. Basically, if you're already using TensorFlow, the previous two notebooks, you're already doing what we just showed you here. Okay, it's just that we're making it explicit for those who are basically coming from more of a Spark background, and you're jumping into TensorFlow from there. Okay, so then, like we had noted, under the TensorFlow, Spark, TensorFrames, LMI section, basically here's what TensorFrames does. It is a wrapper around TensorFlow for the purposes of if you are trying to work with the data that already exists in Spark, number one, or number two, you are trying to determine the hyperparameters. Okay, so in other words, just like what Tom and I were talking about before, and what Joe was talking about before too, is that you don't know what values you're going to use for those hyperparameters. Since you don't know what they are, you're going to try lots of different things. Well, you can either, like the UI, manually change the bias, right, and apply that to a million things, or you can automate that process. So the context is that you can automate that process by using TensorFrames to basically help you calculate what a lower loss function is going to look like and calculate what's the optimal set of hyperparameters for you to work with. Okay, so that's that context. And let's see. So then when you look at TensorFrames itself, basically it's just this code here, okay? So basically I'm first, for those again who are more Spark related, this cell, all I'm doing here is saying, okay, I'm going to import TensorFrames and I'm going to create a data frame. A data frame is analogous to a table. So how many of you guys know pandas by chance? Okay, excellent, thank God. Okay, so. All right, so basically it's analogous to a pandas data frame, okay? It's not. Pandas data frame is actually really freaking cool, so I'm not gonna say it's the same thing. What the data frame within Spark is analogous to it, but it allows it, it's very well designed from a distribution perspective, okay? So again, when you're talking about Spark's coup de grace, its main focus is about distribution. Okay, so I know plenty of people who will then do all their processing with their data, and once they're done, they'll actually go back and put the Spark data frame into a Pandas data frame, so they can run their queries using Pandas. That's completely cool, and provided that you're not dealing with a massive, large amount of data. Okay, I'm talking like the tens of millions, hundreds of millions. Provided you're not doing that, we go for it. Yeah, run pandas, run scikit-learn. I think that's an awesome thing to do. So no debate on that one. Okay, but basically, I've just created a data frame, a Spark data frame, not pandas, Spark data frame here, and this is just what it looks like. Okay, it's really boring. Okay, x. Here's the numbers, 0 to 9, okay? Yay, okay? So, all right. So then if I want to do an addition, okay, basically a tensor graph, okay, basically I'm going to do a block by block addition. So the context that we're coming from is that even though it's not obvious when you're looking at this because it's really simple code, all I'm doing is this, like, I'm doing TFS block, and I'm doing an add, and I'm doing a map blocks, okay? For something this small, this should have just been done in Python. Okay, you should never have bothered doing this in Spark. Okay, but the context and the reason why we're doing this is because in this case, block is referencing Spark block management. Okay, so when you're working with Spark, you're dealing with lots of data that's distributed across multiple nodes. Okay, when each piece of data that you're dealing with, a chunk of data, basically is a block of data. So what we're doing is when we're doing the additions or multiplications or whatever it is you're doing within the context of Spark, you're doing a block by block calculation. That's where this map blocks comes in here, okay? So it'll be fundamentally more efficient when you're dealing with that large amount of data to perform the calculation block by block as opposed to performing it one cell by one cell. Okay, especially because this data is distributed across multiple nodes. Okay, so that's the key facet here of TensorFrames. The thinking is a little weird. If you are not coming from a Spark perspective, you're not coming from a distributed computing perspective, this seems like an inefficient way of doing things, and you are correct. Okay, all right? But for those who are actually used to working within the context of distributed computing, this is the most efficient way of doing things. That's the context here, okay? And then now that we've done it, I can basically just output the data frame. And then, yay, not terribly complicated. Again, for this small amount of data, I just added 3, but again, this is now done block by block. So that's what this particular output is showing right now, okay? And the key aspect, no, so we did not show an MNIST example for this one just because we ran out of time to write it. But basically the context is a lot of the functions that you're going to do when it comes to interacting between TensorFlow and Spark are really element-wise calculations, element-wise sum, element-wise multiplication, things of that nature, okay? And so basically the context of this particular code is that, okay, number 1, I built the data frame. Number 2, I actually now, because I'm going to be dealing with a massive amount of data potentially, okay, I need to actually build a schema. I need to tell it what the sizes of this data is so I can efficiently tell Spark how to distribute the data across the wire and have TensorFlow actually, there was one question that was saying, can I make sure that when I'm running a tensor operation, I don't cut it at the wrong edge? Basically, that's the whole point of this, these set of tasks here, that I actually will only work within the context of that particular piece of data, okay? So in this case, if I look at the print schema of the data frame, you notice that actually I have no idea what it is. It's double, but I have no idea what the size is. So again, common within the context of Spark, you're going to run the TFS analyze. Now again, it's a small amount of data for here, but when you're dealing with a massive large data, you want to be able to know what the array size is. And so that's why running TFS analyze is important. So before Spark tries to make sense of this, before it tries to distribute it, it actually knows the size of the data that you're dealing with, okay? And then that's what basically just analyze this portion of it. And then finally, I can do the element-wise sum and min, excuse me. And so basically this code base right here, basically that's it, okay? Execute the tensor graph. Basically now I'm doing this block by block. That's it, okay? And so a lot of the APIs are completely available at TensorFrames, tensorframes.github.io. So basically, you can look at all that's available here, but we've actually put a lot of the key examples right here for you to work with. But basically, once you've done that, then you actually can return the element-wise sum and min from your Spark data frame pushed into TensorFlow, extracted out back into a data frame for you to play with again. Okay? And so again, it's a very elementary example, but the context is that most of the time when you're dealing with any data, if it's a large amount of data, you're going to have to start playing on the distribution side of things. So TensorFrames basically helps that within the context of Spark. You can throw the data into TensorFlow, do its magic. Once you get the output of TensorFlow, you want to do something with that. Your action is, okay, I see the number 9 correctly. Okay, that means I'm going to go I'll trigger something else because I'm running, for sake of argument, a machine learning algorithm downstream, or I'm running Spark streaming downstream. So now I'm actually able to do that, okay? So I think that's it for this section. Yes, questions?
So in the background, what's happening is like this matrix vector multiplications are just being basically done in distributed fashion when you use TensorFlow TFS, right?
Correct.
What's happening in the background?
Yeah. So let me just repeat what you said first. So in the background, what he said is in the background, I'm doing the calculations in a distributed fashion via TensorFrames, but it is interacting with TensorFlow. That is correct. Yes.
So TensorFlow
okay, cool.
is essentially the engine that is doing all the computation.
Yes.
Yeah.
Okay, cool. Yes.
Does the analyze operation give you the block size, or you got to determine the block size yourself?
If you want to know the block size, you will have to determine that yourself. But most of the time, you actually don't. Basically the Y size of the matrix is all you actually need to know, because it's purely there, so that way Spark itself knows how to distribute it. So you yourself actually don't need to know this information. It's just more a matter, you got to run it, so Spark is now aware of this. That's the key aspect here. Okay? Yes, question there.
So when you say parallel training to determine optimal hyperparameters, is that some sort of automated hyperparameter
able to look at different parameters and make decisions. That's what you want.
So the question is, are we talking about an automated fashion, or are we talking about actually manually changing it? And in fact, actually, I would say it's more of the latter, which is manually changing it, but it actually allows you to get to the automated. Because in the end, the output of those various hyperparameters is a loss function ultimately, right? Which is basically, you're just trying to hit the lowest number. There's an interesting supposition by Andrew Carthy about the fact that in most machine learning and deep learning cases, the local minima, the one that we thought that was going to screw us over basically, in fact actually isn't nearly as bad as we think it is. And so just as long as you're throwing enough hyperparameters at it and you're running it long enough, you'll actually get past the local minima and it'll actually hit the global minima. Okay, so I had to felt uncomfortable saying that. Like I was not used to that idea, but from a lot of the Carthys and a lot of other these deep learning like Zions, these awesome guys and gals who understand this stuff, basically they've come to the conclusion, at least from a neural network perspective, the local minima wasn't actually nearly as big of a problem as they thought it would be. Yeah, so you are right, it will get to automated, but you still have to sort of do a little bit of it yourself to get there. Yeah, okay? Cool. Question there. Okay. Okay. I'm going to repeat your question so everybody can hear it, and make sure I get it right. Okay. So in the context of GPUs, where is the data lying? Is that correct? Perfect. Okay. Within the context of GPUs, the whole reason why GPUs was problematic in the past is that number one, they were relatively small, so they could only hold so much memory. And number two, when you were doing a mem copy from the CPU to the GPU, that took up so much time that basically you were hosed, okay? A lot of the work that was done in the last 6 or 7 years basically allows us to do the string copy, mem copy from the CPU directly to GPUs extremely quickly. So long story short, the answer is the data is now residing on all the nodes, or I shouldn't say all the nodes, whatever Spark decided, on whatever nodes Spark thought it needed. It will then be, the data will reside in memory there, and it'll be accessed. If you've enabled GPU support, it will then put the data into GPUs. So the GPU will do the calculation for you as opposed to CPU. Every demo that we've done today is admittedly enough doing CPU, mainly because I wanted this to be free for everybody. But by the same token, if you were to enable GPU support, or if you ran this on your own cluster with GPU support, then that's exactly what would happen. Yeah, so basically from a Spark perspective, last year we had basically put in all the extra code to ensure that we could, number one, recognize GPUs, and number two, basically put it there, not just in a single fashion. That was what we did late last year, but early this year also to put it in a distributed fashion. So if you had multiple GPUs on a single box, we'd actually be able to go ahead and use multiple GPUs for the calculation as well. Okay, cool. Yes?
It's a roadmap question.
Sure.
Roadmap Keras running on the top, and the TensorFrame and TensorFlow on the back end.
So the question was roadmap on Keras. I can honestly not tell you what the roadmap for Keras is right now. It's definitely a very, very, very popular deep learning tool. So yes, I think you guys definitely, if you're interested, Keras is something you definitely should keep up on. From a TensorFrames perspective, actually come join us. We are actually actively writing the code to basically take on more of the TensorFlow API to make it easier for the two to work together. TensorFlow, yeah, that's easy. Just go to Google's site and you'll see the TensorFlow roadmap. Yeah. So, yes.
Have you looked at Sonnet at all?
Sorry.
Sonnet.
Doesn't ring a bell.
I'm sorry?
It's out of DeepMind.
Is Sonnet Google DeepMind? Yeah, no.
Yeah. I haven't seen that one. No.
Yeah, sorry, no, afraid not. Sorry. Yes?
Are there any plans to also use Keras or other deep learning frameworks?
Oh, actually, yes, I forgot. Good point. And he reminded me and I completely still spaced out on this. Okay, so in the slide deck here, when you get past all this other stuff, you go to the finale part. We have a whole bunch of really good references that we've actually interlaid in here, because these people are fundamentally smarter than we are. Okay, so definitely read up on some of this stuff. One of them actually is exactly this: integrating deep learning libraries within Apache Spark. That actually, so basically, Databricks open sourced as part of Spark Summit this year. the deep learning pipelines, and the first two, the most important two, were TensorFlow and Keras. So yes, so basically they're already integrated. You're more than welcome to go use it. There's actually some pretty decent documentation already written up on how to use both. But conceptually, it's very similar in terms of how to interact with Spark with Keras. It's very conceptually similar to how TensorFrames operates with TensorFlow. Yeah. Okay.
So would you say the distinction is TensorFrames lets you go a little bit more into the weeds with details?
Yes, the supposition is that does TensorFrames let me go more into the weeds? Absolutely, because from a distributed engineering perspective, it's awesome when I can go ahead and do the data science, I can run the deep learning models, but at some point, this becomes too large, and I got to understand how the data is distributed, because the single node itself will break. As simple as that. So understanding both the concept of deep learning pipelines and TensorFrames allows us to go ahead and actually start manipulating some of that. Yeah. Yeah. Okay. Cool.
Cool.
Yes?
So after your learning, you got a successful learning, can you actually go back to look at the feature and kind of to evaluate when you start, can you kind of to see which feature is more important than others?
Absolutely. So in machine learning lore, that's basically like you're running PCA for sake of argument, right? But basically, you have now more than enough data in your network to basically go back, identify which set of features that actually were coming into play. And this is actually when we start going.
Yeah. When we show the demo, when we were saying, okay, this particular feature is recognizing faces, the other one is actually learned to recognize the text.
Yeah.
Right. So that's pretty much. You would have to dig deeper, and that's why I was referring to neural networks being more of a black box a little bit in that sense, because you have to actually write stuff on top of that in order to extract that information that is normally given to you by running a statistical model. But with neural networks, it's doable, but it requires a little bit more work.
Exactly. Yeah. And sorry, question in the back. Sorry. Yes, so in other words, for all you guys who are using the Databricks cluster, the clusters will shut off automatically, but because you have an account, all the data is saved. So you actually have nothing to worry about. It's in fact, actually, one cool feature that I completely forgot to show you guys is that if you decide to go ahead and change it, click on revision history, and actually the whole revision history of your notebook is actually kept here, so you can go back to the one that actually you didn't screw up on, because I am absolutely guilty of doing that regularly. So,
as we all.
Yes. So. Yes. Okay. Cool. Cool. All right. Well then, hey, thanks very much, guys.